Okay, not really changing gears here, but changing how we're approaching these different problems. In this one, we're going to talk about Hess's law. And Hess's law is a very useful law that was noticed by a guy named Hess, strangely enough, you know? Okay, good. Now I've got a reaction written up here on the board. And what this is the burning of methane. And when methane is burned, it's going to give off carbon dioxide and H2O. Now, if you know anything about methane, methane is also known as natural gas. Okay? So natural gas burns, and we know that it's exothermic, because when it burns, it allows us to heat our house, or it allows us to move our forklift or our truck or something like that if you've got a natural gas burning vehicle, something like that. Okay? So that's methane, when it burns with oxygen. What we'd like to know is how much energy it's going to burn in a specific way that we can always identify and quantify what that's going to be. All right? So our unit of numbers of material. So if a certain number of methanes burn, how much energy are they going to release? Well, a certain number of things that we use in chemistry is called the mole, right? So if I have 1 mole of methane, how much energy is going to be released? Okay, and that's going to be our enthalpy value for the system. So we're looking for delta H here, okay? And the delta H we're going to calculate is for kilojoules per mole. And the way this is measured is using a calorimeter. So they analyzed this particular energy value using a calorimeter. So they were able to measure this, and they got a value of minus 890.4 kilojoules per mole. All right? Now that's not Hess's law. What this is just straight up thermochemical calculations. Every time we talk about the mole here, we're talking about a mole of methane that's being burned. We always talk about moles as the least number of moles that's in the reactants, okay? Because if it was a 2 there, we've got to divide this value by 2, okay? It's the least number that's to be associated with it, okay? Not about the oxygens, it's about the lowest number. So when I talk about burning methane, and this is my value, kilojoules per mole, notice that I get different states associated with this thing. I get gaseous carbon dioxide, and I'm going to get liquid water here. Now Hess looked at it and said, well, that's all nice and good, but what happens if you get gaseous water? What's going to be the overall equation? So what he wanted, and I'm going to write down here, I'm writing it down here for a reason, is he wanted to figure out what's going to be this reaction. I should have put gas here for methane. And that goes to CO2, gas, plus H2O, gas in this case. So Hess looked at that and said, all right, well, let's look at that. And so he had some grumbling from the experimentalists that are around, because the experimentalists looked at this and said, well, you know, Hess, we do this thing and we get liquid water out. We're not going to get gaseous water out, so we've got to figure out some other way of doing it. Hess said, fine. That's exactly what he said. He was actually recorded on tape going, fine. No, not really. But what he did say is that maybe there's another way of figuring this out. And what he did is to say, well, if there's a certain amount of energy that's required to put water into that gaseous state, I'm sure we've already measured what that value is. And sure enough, some enterprising people had already done this. They're taking water, which is in its liquid form, and heated it up, and what they got out was water in its gaseous form. Okay? And the energy that was required to turn liquid water into gaseous water was a positive 88.0 kilojoules per mole. So Hess looked at this and said, okay, since I know both of these terms, if I combine them, I can add or subtract these values, whatever it needs to be done, in order to get the delta H for this down here with the gas. So Hess did that, and he noticed that what this does is this removes, because this is on the reactants, this particular part, the water cancels out with this water, so I get an overall reaction of methane and oxygen on the reactant side, and I get carbon dioxide and water, both of them gases, on the product side. So the delta H value that I end up with is a composite of the two energy values that we already know in these reactions. So, how do we figure that out? Well, if we take 88, add it to 890.4, okay, this is a negative, and this is a positive. So, basically, this is going to be a less smaller negative number. And what we end up with is a value of negative 802.4 kilojoules per mole. Okay? So this is an addition of both of those functions. Hess's law is also good for reversing terms. Okay? You notice that if I'm going to reverse a term, the thermodynamics can't really change. So the energy that goes in has to be the same, just with the sign change. So if I was to combine water as a liquid plus carbon dioxide as a gas to make two oxygen gases and methane, my delta H value here is going to be positive 890.4 kilojoules per mole. Okay? And since this is a molar value, if I don't have as much of these moles here, if I say I've got a half a mole, I'm going to have half the energy that's associated with it. Okay? So Hess's law is very powerful in the fact that I can mess around with and change these reactions in order to get this information. So let's do an example of Hess's law and see how powerful it is. Okay, so down here on the bottom, I've got my overall target reaction. So I asked myself the question, I am looking at how much energy is going to be released or required to take the allotrope of carbon, graphite, take two of those, react it with hydrogen gas, and get myself out acetylene. Okay, why am I doing this? Well, for one, acetylene is a very useful material, and graphite's pretty ubiquitous. There's that word again, I like using ubiquitous. But graphite's in a lot of places. It comes out of coal. Okay, so graphite is one of these carbon-rich materials. So again, it's in your pencil. If we can take pencil lead and turn it into acetylene, we can make a lot of torches. Okay, so here's a general idea. I want to know how much energy it's going to take for this particular reaction, or how much energy is going to be released if it's an exothermic process. So what I'm going to do is I'm going to look at some other information that I just happen to know. Okay. And one of the things that I know is that if I have graphite, it reacts with oxygen, it's going to make carbon dioxide gas. So, C graphite plus oxygen gas goes to give carbon dioxide. Okay? And what I'm going to do over here in red is I'm going to report what the delta H values of those things are. Now the delta H value in this case happens to be negative 393.5 kilojoules per mole. Okay? Good. All right, the second thing I happen to know is our famous reaction. If I take hydrogen gas and react it with half a mole of oxygen gas, I'm going to get water out. And the reaction that I have here is this one gaseous. No, it's liquid form. Okay. Whoa, that's an L, believe it or not. L, there you go. Okay. This is minus 285.8 kilojoules per mole. Is that a surprise to anyone? If you've ever seen two hydrogen balloons and an oxygen balloon mixed together, set on fire, they're going to explode. There's a big flash of light and a burst of heat. So that's not a surprise to anybody. Okay? The last one I know is that when I burn acetylene gas in the presence of oxygen, so 2C2H2 gases plus 5 oxygen gases, what I'm going to get out is carbon dioxide and water. And I know some of you are asking the question, are these subscripts important? The answer is yes, they're incredibly important because everything has to match. Otherwise, your thermodynamic information is wrong. Okay? All right, the amount of energy that comes out of this one is a staggering minus 2,598.8 kilojoules per mole. All right? So those are the three equations that I'm going to use to try to get my overall equation down here on the bottom. What you need to do first is make sure that the things that you want are on the right side of the equation. So down here I've got graphite. Is graphite on the reactant side of the equation? If you look up here, graphite is on the reactant side of the equation. That's good. Is the amount of graphite here the same as the amount of graphite that's down here? I've got 2 here, and I've got 1 here. Okay? Before I put a 2 where that graphite is, I need to look at every other step and make sure graphite doesn't appear anywhere else as well. Because if it does, then I'm going to have a possibility of adding that extra 2 from a different step. Fortunately, I looked through my equations that I've chosen. Graphite's not there. Okay? Which means that there's only one solution here to this problem, and that's multiplying this guy by 2. So I have to multiply this one by 2, which means that my energy over here has to be multiplied by 2 as well in order to get the value that I need. Second thing I'm going to look for is H2. Is H2 on the reactant side or the product side over here? H2 is not in the top equation. There's an H2 on the reactant side over here. No H2 over there. So this is my H2. I've got 1 here, 1 here. So this one, I've got a 1-to-1 ratio. Don't have to multiply it or reverse it here. I come over here, C2H2. Now I've got 2 C2H2s over here, okay? And it's on the reactant side, this one's on the product side. So what do I have to do to this overall equation? I've got to reverse it. So I'm going to use the reversing purple, okay? Purple marker at this point, and I'm going to reverse it. So in this case, H2O liquid plus, you know what, I forgot a term. Why didn't you guys tell me? I forgot the 4 and the 2 here. Sorry. 4 and 2, okay. So I'm going to reverse this. So I've got 2 waters plus 4 carbon dioxides goes to 5 oxygens plus 2 acetylates. All right? When I reverse that reaction, the sign here is going to reverse as well. Okay? So now it's gone to a positive value. So now that I've reversed this, I've got this copied down. Make sure that I've copied it down right, and I have. What I'm going to do now at this point is erase this, because I've got to use this particular reversed equation in order to get what I want. Now notice that I have 2 acetylenes over here, and I've got 1 down here. So what do I have to do to this term? I've got to divide this by 2. So divide that by 2, divide that by 2, divide that by 2, divide that by 2. I'll get 1 there. The energy has to be divided by 2 as well. So this entire term has to be divided by 2 in order to get the correct amount of energy for Hess's law at this point. Okay? So that becomes a 1, that becomes a 2, that's still a 5/2, and this becomes a 1. All right? Now, in order for Hess's law to work, I can't have any extra atoms or molecules floating around. Everything has to cancel. Okay? Now over here, I've got my graphite, that's fine. I have 1 oxygen. Okay? Since I've got 1 oxygen here, what I'm going to say is, that's wonderful. Okay? All right, I've got 1 oxygen here, but I multiplied that entire thing by 2. So when I'm multiplying it by 2, I've now got to have 2 graphites, 2 oxygens, and 2 carbon dioxides. So if I look at this, now look at this half, this is 2.5 carbon dioxides, or excuse me, oxygens. 2.5 oxygens, and I've got 2.5 oxygens right there. So guess what? They're equal on both sides of the equation, so I'm going to cancel these oxygens. All the oxygens cancel out. Good. What about carbon dioxide? I've got 2 carbon dioxides here on the reactant side of the equation, 2 carbon dioxides on the product side. Those are going to cancel out as well. Okay? The last thing is going to be water. And I've got liquid water here, liquid water there. Both of those cancel out. All I have left are 2 graphites, H2, and acetylene. 2 graphites, H2, and acetylene. Now I'm ready to plug and chug my numbers and get my mathematical results. Okay, so what I've done is I've taken these numbers down here, just in the to save some time. 393.5 is here. I multiply that by 2, because I put a times 2 over there. Over here, minus 285.8. Took this number directly down here, because I didn't have to multiply it or divide it or anything. This one I had to divide by 2, so I divide this one by 2. Okay, and what I get out is a value of 226.6. Plus 226.6. And that's kilojoules per mole. Don't forget the sign, it's important. Okay? I like to put pluses and minuses to make sure I'm intending to say what I'm saying in thermodynamic reactions. And don't forget your units, because they're important. Because sometimes we use calories, sometimes we use kilojoules, sometimes we just use joules. So make sure that your units are constant and you're communicating in the right units. Because your magnitude could be off if you're using kilojoules and joules, and that would be a gigantic mistake. Okay?